Okay, so far we've learned about different ways we can quantify movement, like measuring position, distance, displacement, velocity, speed, and acceleration. And when we're talking about linear kinematics, there's just one more biomechanical concept that we need to learn, and that's projectiles. So by the end of this final linear kinematics video series, we'll learn about uniform motion and what that means, what a projectile is, and what we can calculate because of a projectile. So in the last video, we talked about acceleration and how it's defined as a change in velocity over a change in time. And in certain situations, the acceleration of an object is constant, it doesn't change. And this is an example of uniform acceleration. So it occurs when the net external force that's acting on an object is constant and unchanging. And if this is the case, then the acceleration of the object is also constant and unchanging. So let's think of a ball that's thrown straight up into the air. And let's try to describe its motion in terms of velocity and acceleration, because we're pro with these terms now. So first, we always set up our coordinate system so that we can give directions to the movements. So here, the x-axis is oriented horizontally in the direction of the horizontal motion of the ball, and the y-axis is pointed vertically or upwards, and upwards is positive in this case. So how would you describe the vertical velocity of the ball if it was starting here and you threw it up in the air and this is where it ended? How would you describe the vertical velocity throughout that motion? So as the ball leaves your hand, it's moving in this upward direction, right? So its velocity is positive. Now, is the ball speeding up or slowing down as it's going up here? It's slowing down in the upwards direction, which means that the acceleration is negative or in the downward direction, right? Because you're slowing down in this upwards direction. Now, when the ball reaches the peak of its flight here at the top, what is the velocity then? Well, it's actually zero, right? That for a moment in time, the ball is no longer moving. And then after the ball is past its peak, it falls back downwards. And so what happens now to the velocity is it's changing directions, which is why there's this brief moment when it's zero, because it's changing from a positive direction to now being a negative direction. So the ball is now moving downwards. Okay, and what about the acceleration? So in this case, the ball is speeding up in the downwards direction. On the way up, it was slowing down, but now it's speeding up, which means that the acceleration is in the same direction as the velocity, which is downwards here. So despite the changes in the direction of the ball, right, it was going upwards and now it's going downwards. Despite that change in direction, the direction of the acceleration was constant throughout. The acceleration was always negative or always downwards. And do you have any sort of idea of what forces would have been acting on the ball while it was in the air to cause this acceleration? So we haven't talked about forces. I'll just give you the answer. The only forces that were acting were air resistance, which is so minimal that it can just be ignored, and the force of gravity, or the weight of the ball. So we don't need to focus too much on forces right now because we will be revisiting these concepts in a few weeks in much more detail. But that just sort of gives you a brief idea as to why the acceleration is always negative, because it's always being acted on by the force of gravity. So the ball in the air is an example of a projectile. And by definition, a projectile is an object that has been projected into the air, like the ball, or it's been dropped and acted on only by the forces of gravity and air resistance. And if air resistance is too small to even measure, and the only force that's acting on a projectile is the force of gravity, then the force of gravity will accelerate the projectile. So the acceleration due to gravity is always, always, always 9.81 meters per second squared downwards. You'll need this number forever and ever, so if you don't already know it, make sure that you memorize it as soon as possible. No matter how heavy an object is, acceleration due to gravity will always be 9.81 meters per second squared in the downward direction. And you might have done this experiment when you were younger about dropping a watermelon and an egg, and they both fall at the same time because the acceleration is the same for both objects. And so the same is true here for this apple, this tennis ball, and this safe. They're all going to fall at the same time, even though they have different mass, because the force of gravity is the same for all three of these objects. So vertical acceleration is equal to gravity, which is equal to negative 9.81 meters per second squared. And remember here that the negative sign indicates the direction, right? So here, acceleration due to gravity is in the downward direction. Okay, so now we know what the vertical acceleration of the ball is. We can use this knowledge to determine the ball's velocity. We know that the equation for acceleration is a change in velocity over a change in time. And we also know that acceleration is equal to gravity. So if we just rearrange that equation, then we can find the final velocity of the ball. And that's what you see here. So the final velocity is equal to the initial velocity plus gravity times the time that it took for the ball to move. And I invite you to look closely at this equation. Does it remind you of anything that you might have seen in high school? It's the equation for a line. So y equals mx plus b, right? Where y is your dependent variable, m is your slope, and b is the intercept. So in this projectile equation, the final velocity is your dependent variable. Change in time is your independent variable, and your initial velocity is your intercept. And then, sorry, I forgot to mention that gravity or acceleration due to gravity is the slope. That's the m term there. Okay, since velocity is linearly proportional to time, because it's defined by a linear equation, then the average velocity over a time interval is equal to the velocity midway between the initial and the final velocities. And this velocity is the average of the initial and the final velocities. So these are the mathematical terms for what I'm saying in words here. And we also know that velocity is displacement over time. So if we use the previous equation and we substitute the final velocity, then we can solve for the final position. And that's YF. There you go. I'm not going to walk through all of this, but basically all you need to know is that by substituting in what you found in the previous slide with your final velocity, you can also find out your final position. Okay, so if you want to, you can go through this whole derivative, but I don't think that it's important for you to know that. So I just wanted you to see where these equations are coming from, essentially. But if you have any questions about the math, then of course we can go through that together. So we've seen the equation for the vertical position of the projectile. That's what I just showed you on the previous slide. And we've also seen the equation for the vertical velocity of a projectile. Now there's one more equation that describes vertical velocity of the ball as a function of its vertical displacement and its initial vertical velocity. So this first one here is the one that we've already covered. Now let's talk about this one here where we're using vertical displacement rather than time. So if we're analyzing the motion of something that is dropped, the equations are simplified. Yay! So for a dropped object, the equations become the following. So for the vertical position of falling objects, the initial position is 0. So that's this term here. We can eliminate y initial. And the initial velocity is also 0 because the object isn't moving yet. So the whole first term here is equal to 0. And the same thing is true about the vertical velocity calculations. If we take the equations we just saw in the previous slide, we can simplify those by removing the initial velocity term in both of these equations because we know the initial velocity is 0 when the ball is being dropped. Okay, so just a little check to make sure that you're still with me here. What is the vertical velocity of the ball when it's at the peak of its flight? It's 0, right? The peak where the ball changes from a positive velocity or going upwards to a negative velocity or going back downwards. Okay. So the symmetry of the flight of a projectile will also help us simplify our analyses of projectile motions. So if you toss a ball up in the air, which one is longer? Is it the time that it takes for the ball to reach the peak or the time for it to fall back down? Well, I just said that symmetry is important. So the answer is that the time intervals are the same. So the amount of time that it takes the ball to go up is equal to the amount of time that it takes for the ball to fall back down. Okay, that's math right there to say exactly what I just said. So the change in time on the way up is equal to the change in time on the way down, if the initial and final vertical positions are the same. That's a pretty big if. So this change in time on the way up being equal to the change in time on the way down is only true if the initial and the final positions are the same. And then similarly, the total flight time is equal to 2 times the time of the up phase or 2 times the time of the down phase, right? So the total amount of time that the ball is in the air is equal to 2 times either the time up or the time down. Okay, so now that we can describe the vertical motion of a projectile that's moving only up and down, what about the horizontal motion now? So if we throw a ball in the air from one hand to the other, what forces are acting on the ball? If we break it down into horizontal and vertical components, we know that gravity acts vertically downwards on the ball, but what about horizontally? Are there any external forces that are pulling or pushing sideways against the ball to change its horizontal motion? The only thing that could exert a horizontal force on the ball is the air through which the ball moves. But I've already told you how minimal this force of air resistance typically is. So that means that the horizontal velocity of the ball should not change from the time that it leaves your hand until the time that it contacts your other hand. So if there's no change in velocity, there's no acceleration. So the acceleration in the horizontal direction is 0 in a projectile motion. There is no horizontal acceleration. If the horizontal velocity is constant, then the average horizontal velocity of the projectile is the same as its instantaneous horizontal velocity, right? It's never changing. And since average velocity is displacement over time, then displacement is equal to velocity multiplied by time. And so by manipulating the equation, we can isolate the final horizontal position of the object. That's this equation down here. So if our coordinate system is set up in such a way that the initial horizontal position is 0, then the equation is even more simplified. The horizontal position, the final horizontal position, is equal to velocity times time. So this recap slide is just to match the other recap slide. I think it was slide 11, where we looked at vertical position, velocity, and acceleration. Here on this slide, we're looking at the horizontal position, the horizontal velocity, and the horizontal acceleration. Okay, so now to give you an even more general recap of the past few slides and the countless equations that I just threw at you, there are really just four key equations when you're solving projectile equations. And I've put them in a cute little box here for you. So we have equations for vertical position, for vertical velocity, two of them for vertical velocity, and one for horizontal position. And in each of these equations, if two of the variables are known, then the equation can be solved for the third variable. And the trick is to first determine what variable you're trying to solve or determine, and then you want to identify what two variables you know, and then just use that corresponding equation. And the vertical and horizontal components of projectiles are independent of each other, as we've seen. They have their separate equations so far, but there is one equation that can be derived to describe the path of a projectile in two dimensions. So combining those vertical and horizontal components. And that's the equation here. So this equation just comes from the substitution of the horizontal position equation into this vertical position equation by isolating delta t and replacing it. So you can work through the derivation if you want, but honestly, you just need to know that this formula combines the horizontal and vertical components. So examples of projectiles in sports and in human movement are countless. These are just a few examples, but basically any ball that's used in sport becomes a projectile once it's thrown or it's released, if the air resistance is negligible, of course. And once a ball has left our hands and it's in its flight, then our actions and antics cannot change its predetermined course or velocity. So it seems pretty obvious that the balls used in sports are projectiles, but what about us? Do you think we're projectiles? Absolutely, we are. As soon as our body has left the ground, we become a projectile, just like a ball, and we can't change our course. So, for example, once a soccer goalie jumps out to the left to block a penalty shot, the path of their body cannot be changed, so they won't be able to change the direction and block the shot if it actually goes to the right instead. In projectile activities, the initial conditions, so the initial position and the initial velocity of the projectile, will determine the motion that the projectile will have. In sports involving projectiles, the athlete's objective when throwing, kicking, striking, shooting, or hitting the projectile, it usually concerns one of three things: the time of the flight, the peak height, and the horizontal displacement. The time in the air of a projectile is dependent on two things: initial vertical velocity and initial vertical position. The peak height of the projectile is also dependent on the initial vertical position and the initial vertical velocity. Now, the horizontal displacement of a projectile is dependent on three things: initial horizontal velocity, initial vertical velocity, and initial height. The higher a projectile is at release and the faster it's moving upwards at release, then the higher it'll go. So I invite you now to think of different sporting examples where you'd want to maximize your time in the air. Something like a football punt, or if you're a gymnast, you're making some moves in the air. Obviously, I'm not a gymnast. And diving, right? You want to maximize the amount of time that you're in the air. Now, what about minimizing time in the air? If you're hitting a spike in volleyball, an overhead smash in tennis, a baseball pitch, those are times where you want your projectile to go from point A to point B as soon as possible. Maximizing peak height, something like volleyball or basketball, where yourself are a projectile and you want to jump as high as possible. Maximizing horizontal displacement, examples of that would be shot put, hammer throw, javelin, long jump. So there are all sorts of examples in sports where these three different components of a projectile are important. Okay, we made it. In this lecture video, we learned about uniform motion and how we can calculate different variables based on the idea of projectile motions where the acceleration is constant and unchanging. Now, I know this week was quite heavy with information, so take the time that you need to absorb the content, rewatch the videos or parts of the videos that were less clear, and make sure that you check your understanding. There were quite a few activities this week. I want to make sure that all of that information really makes sense to you because these concepts will come up over and over again throughout the course. So it's really important that you understand this sort of foundational content this week.